To conquer multi-step equilibrium problems, we need to have a few strategies available to organize our thoughts. One of the most effective strategies is making a rice table, sometimes called an ice table. The R in rice stands for a reaction, or more importantly, the ratios found in that reaction's stoichiometric coefficients. Why? Well, because we're going to need them for any kind of stoichiometry or multiple ratios. The I in rice stands for initial concentrations, or initial partial pressures, but never moles. The C in rice stands for change of concentration or of partial pressures. And finally, the E in rice stands for equilibrium concentrations or equilibrium partial pressures. The E row in our ice table is the most useful because these values or algebraic expressions can be substituted into equilibrium constant expressions. Let's do an example to solidify our understanding of the organization of the rice table. First things first, let's read through this question. At a given high temperature, hydrogen gas and iodine gas will react to form hydrogen iodide gas. Glorious. If the reaction begins with hydrogen gas's concentration being 0.1 molarity and iodine concentration being 0.2 molarity, the equilibrium concentration of the hydrogen iodide is observed to be 0.187 molarity. Calculate the equilibrium constant at this temperature. Okay, to start off a question like this, we need to visualize when all these numbers are happening. So let's make a rice table. The first step in the rice table is writing down the reaction. I know that most of the time the reactions are in the problems, but you're far less likely to make any mistakes with multiple ratios if you have the reaction right above where you're going to be doing all your math. So just take the moment. You can see it really only took us like 10 seconds to rewrite this reaction for R in the rice. Next is organizing all of our numbers into initial concentrations, change of concentrations, or equilibrium concentrations. So I'm going to go ahead, make a table. As a personal preference, I like to put 2 lines where the equilibrium symbol is. And then make general boxes for everybody else. Okay. The words in the stem of the question say that we're beginning with 0.1 molar for hydrogen and 0.2 molar for iodine. So I'm going to put those numbers into my I boxes. 0.100 and 0.200. I feel at this point, because we weren't given an initial value for HI, that I'm going to assume that I didn't have any at the beginning. Several problems will tell you something along the lines of the 2 reactants are put in an evacuated container. That is also another word key to know that those are the only 2 things in there. There aren't any starting products. However, don't get used to that, because in future problems we will have starting amounts for all of our reactants and products. Okay, next let's sort through our words. We have one more number to play with. It looks like the equilibrium concentration of the HI, so I need to put that in my E area, is 0.187 molarity. Now that we have all of our information organized into when those concentrations are happening, we can start to puzzle out what changed. The easiest thing that I'm seeing right now is that we went from having no HI to having a concentration of 0.187. So the change I'm seeing there is an addition of 0.187 molarity. Now I'm starting to think about, well, where did that come from? It must have come from the reactants. And then I remember that I write down my reaction ratios so that I can do multimole ratios. If I have 0.187 products, which have a 2 in front of them in a balanced chemical equation, that means that I needed half as much iodine to get things going. So I'll grab a calculator and do 0.187 divided by 2 and write down the answer of 0.0935. Since there's a 1-to-1 ratio in between the iodine and the hydrogen, I will also subtract the same amount from the hydrogen. Now I'll just grab a calculator really quick and perform the subtraction of the top number minus the change number to get 0.0065 for the hydrogen leftover concentration at equilibrium and 0.1065 for the iodine. Please note, at this point in my question, I am not worrying about sig figs. That's important for most textbook examples. The people who made the keys for these problems used the stored numbers in their calculators to create all of the answers. So you should probably do that too. Do sig fig rounding at the end. Okay, well that was a fun tangent. Totally forgot what we were doing with this problem. Let's reread the question. Let's see, numbers. Calculate the equilibrium constant. Okay, so I need to write down the equilibrium constant expression so that I make sure I don't make any errors. So the K for this guy is going to be equal to the concentration at equilibrium of the hydrogen iodide squared, because there's a 2 in front of that HI. The hydrogen, 1 for that guy because there's a 1 in the balanced chemical equation, and same thing for this iodine. Glorious. Let's go ahead and put in our numbers from the E box. Okay, so we have 0.187 for the hydrogen iodide. We'll need to square that in our calculator. Multiply these two guys on the bottom. And when I punch these suckers into my calculator, I end up with a number like 50.515. I know that I have 3 sig figs and all of my starting numbers in the prompt, so I'm going to chop it right there and say that my K value is equal to 50.5. Equilibrium problems will often start with very different pieces of information, but the rice table can help you organize all of that information into a useful way to figure out all the information you need to know. Please try using this technique for all of your equilibrium problems.